Cool. So thanks for joining and thanks for the intro, Isabel. And now let's talk about how to do root cause analysis in post-deployment data science. So on the agenda today, that is never easy. On the agenda today, we're going to talk about the machine learning model timeline production. So what happens after we deploy machine learning model to production? And then we're going to talk about why models can fail in production, what are possible failure modes, and how we can actually kind of recognize that, find that early, get some kind of early signals of model failure. And then we're going to focus on two kinds of root cause analysis. The first one is going to be root cause analysis for issues that we are able to find and diagnose before we actually get the target data back, so before we get the labels or the ground truth back. And then the second part of the RCA will happen after we get the targets. And that part is going to be significantly smaller because luckily we can actually diagnose most of the issues before the targets arrive. So let's get started with kind of an overview of what happens after you deploy a machine learning model to production. So it's actually quite simple, but it's really worth noticing the kind of chronological order things here and notice what things we have access to and what things we don't have access to before there is business impact and before the business actually takes action and then hopefully profits from the model. So first we get model inputs, model predictions. Based on these model predictions, there's business actions that are taken. Hopefully, of course, if your model is actually in production and business is using it, and then based on that, there's business impact. And if the model fails, we're going to have business impact before the targets arrive, because targets normally arrive either as a feedback from the business action, or they arrive independently after a while, let's say if we do some kind of prediction, like demand prediction. And we have now basically two ways of trying to diagnose early on the issues with the model. First, we can look at estimate model performance. So we can somehow try to estimate the model performance right as a model inputs and model predictions arrive. And then the second one is we can calculate model performance, the actual realized true performance of the model after we get the targets. But if we want to catch failure before it severely affects the business, and before supposedly we actually lose money, we need to do it before the targets arrive. So we're going to be focusing first and foremost on the issues that are triggered due to estimated drop in performance, and then secondly due to realized performance, because we still get more data after that, so it's still very useful to look at realized performance later on. Now, in terms of the workload, it's really quite easy. It's not rocket science. It's barely any science here. It's just good practices. First, we're going to do performance monitoring, and we're going to be always regularly monitoring our machine learning model in production. We're going to be monitoring both estimated performance for the predictions that happened now, and we're going to be also monitoring realized performance for the predictions that happened a while ago as the targets arrive. So if we, let's say, predict something 3 months ahead, then we're going to be looking at realized performance from predictions made 3 months ago, and we're going to be looking at estimated performance for the predictions made today. If we observe that there is a performance drop, then we're going to trigger the main topic of our webinar today, the root cause analysis. And then based on that, we're going to have some specific issue resolution step that I'm going to touch upon very briefly today, but the main focus is going to be on the root cause analysis. And of course, if we don't see drop in performance, then we don't need to trigger anything. Just keep on monitoring performance day to day or hour to hour or week to week, whatever is our cadence. Now, in terms of the actual two flows for performance monitoring, I could already cover that. Before targets arrive, we're going to focus on performance estimation. If we see a drop, then we're going to be able to use 2 out of 3 tools that we have available at our disposal for root cause analysis. And these tools, broadly speaking, are data quality issue or data quality detection and covariance shift detection. And then we're going to be able to narrow down, hopefully in most cases, what exactly went wrong, what exactly changed in our data such that model doesn't make good predictions anymore. And then we can go to issue resolution. And after targets arrive, there is one big part of what can actually go wrong with models in production, which is concept drift. And then we're going to be able to look at it after we get the targets, because then we can see whether there is concept drift. And then based on that, we're also going to go into issue resolution. Now, why models actually fail in production? I already kind of covered the 3 main cases, which is data quality, coverage shift, and concept drift, but let's look at it again here. So first, in terms of data quality, it can be basically defined as an increase in incorrect or incomplete features, or also unseen features. Something is wrong with the actual data. And here I want to really stress the fact that it doesn't mean that all data needs to be correct. Data quality here we define as an increase in incorrect data or missing data. So we might have, let's say, 5 or 20 or even 80% of the data missing during our testing, and that's completely fine. After we deploy the model to production, if we still keep the same rate of missingness for our data, that is not a new data quality issue. We wouldn't see it as a data quality issue from the perspective of monitoring. From the perspective of monitoring, we're looking at something that changed in our data quality situation that caused the model to degrade. So here an example, you have an unseen feature or unseen value where when we look at the clove sizes, we used to have L, S, M, M, etc. So we only had 3 categories. But now as the model gets released to production, we might have a new size or a new value there that was not seen. And we wouldn't expect a model to deal with unseen categorical feature very well. So that would be a data quality issue. Now, the second issue here, or the second reason why models can fail in production, is covariance shift. Covariance shift is simply change in the joint feature distribution. So if we look at one-dimensional feature, one feature or one-dimensional model input space, if we just observe a change across that distribution, we're dealing with covariance shift. We have a lot of materials about how covariance shift can specifically impact performance here, but for now, suffice to say that it is not possible to immediately say, just based on covariance shift, whether performance is going to be impacted. We need to really look at how it works with the model, or how it, let's say, it's interwoven with the model, and whether the data has shifted to more or less easy to predict region. And that is something that we are able to do with our performance estimation algorithms, so that we can quantify the impact of covariance shift on model performance. And this is kind of the main thing we're using to get early signals of something going wrong. Then we have concept drift, which is a change in kind of conditional distribution of the targets conditioned on our features, or in plain English, change in the relationship between the target and the features. And again, here, if we look at pure concept drift, we're not observing any change in the distribution of the features, but we are observing the change in this conditional probability, which means that even if model inputs will look the same, the actual targets will look different. And this is something we cannot detect with performance estimation, so we'll have to rely on realized performance, and we'll have to wait until we get the target data to really see whether there is some kind of concept drift, and then resolve it later on. So, kind of in a nutshell, we can detect data quality issues and covariance shift issues before the targets arrive, and these are luckily the two most popular causes for drop in machine learning performance. And we cannot detect concept drift, so we can only do that when the targets arrive. Now, in terms of root cause analysis, let's focus on the first two causes, data quality and covariance shift, because it's something we can do before targets arrive. Why we can't rely on realized performance or calculated performance? I mean, it's very simple. It's because we don't have the targets. So if we are predicting, let's say, a few months ahead, and we deploy our model to production, we will not know what is our level of performance. Because of that, we can also not rely, unfortunately, on data-driven detection tools or covariance shift detection tools. Here, you can have an example of PCA reconstruction error, which is a quite powerful multivariate drift detection tool that we have in our product and our library. And still, we see that sometimes we're going to have a lot of alerts. There's going to be a significant change in the data structure that does not correspond to change or decrease in model performance. So we're going to be dealing with a lot of false positives if we just rely on data drifts, and also, unfortunately, false negatives, where we might actually see no significant drift in our covariance, but there's going to be sometimes a drop in performance. This is luckily quite rare. Most of the time, the problem is that we're going to be just drowning in false positives and false alerts. So we need to actually focus on performance estimation directly and not just on data-driven signals. And the way performance estimation works is already briefly explained, and I'm not going to go deeper here in this presentation, but we're going to just use it as a signal that allows us to quantify the impact of covariance shift on model performance. So what you see here is that we can actually estimate performance for any data point for which we have model inputs and model outputs. And that's what we're doing. And we're seeing that we're observing a drop in performance. So kind of summarize why performance estimation is important. It is an immediate, and it really is an immediate warning sign that something is wrong with our model. It's something that we can do as the model makes the prediction before even the actual prediction reaches the business side and before the decision is taken. So it's something that we can actually act upon just as we finish processing our batch of predictions, or the same if we use streaming. It allows us then to act and fix issues before negative business impact, or before there is significant business impact, negative business impact. Even if the business decisions are taken automatically, we'll be able to capture and stop any issues, let's say, hours from model degradation, instead of waiting potentially months or years until the targets arrive. So as far as comparing that to looking only at realized performance, is basically an immediate action. And doing root cause analysis before the targets arrive is really only possible thanks to performance estimation. Now, let's say that we have an issue, we detected a drop in performance. What do? We're going to look at our covariance shift toolbox, which is basically all the algorithms and all the methods that we can use to figure out what is going on with our data, how are our model inputs changing, and let's delve deeper here. So basically, we have two types of detection. First, we can look at univariate detection, which is summary statistics, and the actual univariate detection methods that will just tell us what is happening with a single feature. And then we have multivariate detection, where we have two algorithms that allow us to detect change in the data structure. I'm not going to go too much in depth into any of the methods here, because again, we only have 45 minutes here, but we have open documentation about any of those, and we're going to be picking and choosing specific algorithms here as an example of how to do root cause analysis. So the actual covariance shift flow, which is a part of root cause analysis before the targets arrive, looks as follows. We're going to look at each feature one by one. So we're going to we can of course do it automatically in AnyML, and we can only sort by the features that have alerts. And what we're going to do is we're going to run Jensen-Shannon distance metric, and we're going to see whether there is a significant increase in that metric in a way that there's actually an alert on it for the time when we observe drop in performance, which is preferably the last chunk of data, because we want to act as fast as possible. And if we see that there is significant drift in that feature, then I'm going to look at the summary statistics. We're going to look at average, median, and standard deviation specifically. If we see a change in any of those, then we can just say it's a simple drift. Our median has changed, or a mean has changed, and it's something that's normally going to be very easy to interpret from business perspective. If somehow, and it's actually possible, we see that there is a change in our distance metric, like Jensen-Shannon metric, but the summary statistics don't change, then we're going to have to look at the distribution plots that I'm going to show in a while, and then we're going to deal with some quite unusual covariance shift, but it's something that we can still quite well explain. And let me go through an example here. First, we're going to look at a feature. We see that this feature increased significantly after we put them on production. So there's definitely an issue here. And then if we look at summary statistics, we see that basically the entire drift that we observed due to the Jensen-Shannon distance increasing can be kind of explained by just change in the average. So we can already say the average has changed. We're going to look at that feature and see what's going on there from business perspective. Then, kind of from an opposite perspective, we can look at, again, different feature, and we see equally strong increase in Jensen-Shannon distance, but the average and then also other summary statistics might actually not change. And then what we have to do, we have to look at so-called joy plots, which look very cool and they're very pretty. The reason for the name is different though. Let's not go into details here. And let me just say that we see that the actual distribution of the data has changed. It used to be, let's say, roughly normal distributed, and now we see something that looks more like a uniform distribution that gently falls off. So this is potentially data quality issue, potentially covariate shift issue, but we're definitely looking at it and we already understand what's going on, and we can start digging deeper into what actually changed in that feature using our use case knowledge and the business knowledge we have. But unfortunately, univariate detection is not always enough. It allows us to capture like any change in a specific feature, but sometimes might be that none of the features actually, the distribution of none of the features actually change in a meaningful way. And yet we see a very strong and significant change in data structure that impacts performance. And here is a very simple example of why that might happen or how it might happen. And what you see here is basically we have two very strongly correlated features. And we see that after 6 weeks, they are again very strongly correlated. And the distribution, if you look at the distributions here on top and on the right side of the plot, you see that distribution before and after, so at week 10 and week 16, are basically exactly the same. And yet, if we look at the distribution from the two-dimensional perspective, it's completely different, and it probably affected performance very much. And just to kind of showcase that indeed univariate detection tools on that dataset will show nothing, but multivariate detection with PCA reconstruction error will show an incredibly strong change in the PCA reconstruction error, so our drift signal, and it's something that we can then look at and say that there is a change in the data structure. So then we look at the kind of second part of our covariate shift flow when we look at the subset of features for where there is no change in the distribution, and we'll look at whether there is a change in data structure there that cannot be captured or explained by univariate drift. And this kind of concludes just to give you an example here, indeed, this kind of concludes our approach to covariate shift detection and the root cause analysis when it comes to covariate shift detection. And now, before I give you a full summary, let's look at the data quality, which is also another thing that we can do before the targets arrive. And here, our toolbox is quite similar, but in a way a bit more limited or more focused. Again, we can look at summary statistics. They're also really good at detecting changes in the data. We can also look at specific univariate drift methods, specifically L-infinity and Wasserstein. And both of these methods tend to be quite sensitive to outliers. And this is exactly what we're going to use them for outlier detection. And then we also have some quite simple data quality tools at our disposal when we'll be able to look at unseen values that I already mentioned briefly before, and just the ratio of missing values and how it happens, how it changes in time per each of the features. Now, the flow here is significantly simpler, and we can also parallelize this. So what we're going to do is we're just going to look at summary statistics. We're going to be looking at sudden changes in the data. And if we see that, then we see that there is some kind of offset in the data, which is probably a data quality issue, because we will very rarely see that kind of change naturally or organically. We'll look at Wasserstein distance. And if we see that there is significant increase in Wasserstein distance, then we are quite likely dealing with outliers, especially if we don't see an increase in JS distance. We're going to just look at the new unseen values or the ratio of unseen values. And if they go above 0, then we'll probably have some anomalies in our data, something that shouldn't be there. And then lastly, kind of a trivial thing, we're going to look at the ratio of missing values in time. And if we see a significant increase in the ratio of missing values, then missing values are a problem. Quickly going over how it looks, if we look at our summary statistics and average just kind of jumps in a very strong way from one chunk to another, that probably means that something up there in the data pipeline, either the unit changed, if the unit changed, for example, from kilogram to pound, or the other way around, or the currency changed from one currency to the other, then we would expect this kind of jump in the data, which is, of course, something that the model cannot deal with because the model understands kilograms, not pounds. So it's something that we'll have to look into. Or somebody might have multiplied a specific data point by 2 instead of 0.2, and we see a strong jump in the average values of a feature. Then outliers, again, we're just looking at Wasserstein, and because it is so sensitive to outliers, if Wasserstein increases significantly more than Jensen-Shannon distance, then we're most likely dealing with outliers, and we have to look at it on kind of instance level basis when we try to find specific outliers. And then unseen values, again, if it goes ever basically above 0, because by definition, we're going to make sure that all the values in the reference data are unseen by definition. So if we see any new values, that probably is a core cause for a reason to be alerted or some potential data quality problem that we need to investigate. And then missing values are self-explanatory. Now, let's summarize. I'm gonna let you look at this quite advanced graph for a second and take a sip. Yeah. So on the covariate side, we start with univariate drift. If we see that there is change in univariate drift, then I'm gonna see whether we can just say that it's due to change in median, mean, or standard deviation. If not, we're gonna have to look at the actual distribution plot and see what's going there. If we see no change in univariate drift signals, so we don't have any alerts for Jensen-Shannon distance, then we're going to look at multivariate drift. If we don't see anything there, then there's no covariate shift for that specific feature or subset of features. If we do see a increase in multivariate tools detection, then we have structural drift. The data structure has changed. And for data quality, we already went over that. The only important thing here is that summary statistics should be really used differently when we're not looking at just gradual changes, but we're looking at sudden changes that we would not expect from an organic process. That's kind of it when it comes to root cause analysis before the targets arrive. Now let's talk about how to resolve those issues. And resolving those issues is actually quite easy in terms of the process. Of course, actually doing it is a completely different kettle of fish. And at some point, I'm going to do a webinar that focuses on that. But right now, we're going to just have a TLDR kind of version of that. And if we have covariate shift, we can do three things. We can either adjust the model. Sometimes it might be possible to change which features are ingested by the model. If there is a lot of collinear features, and we can focus on more stable features, which might improve performance of the model. We can just adjust the prediction thresholds for classification models. Of course, we cannot do that for regression models, but for classification models, if we care significantly more about recall than precision, for example, we might just adjust our classification thresholds to kind of protect one of those two. Let's say we can protect recall and sacrifice precision, which allows us to still provide good business impact or reduce risk. That would be unacceptable from business perspective. So it's something that we can do immediately before the targets arrive. And this is a really cool thing, because if we see that, let's say, our recall needs to stay above 60%, and we see that it starts dipping below that red line, then what we can do is we can just adjust the prediction thresholds to make sure that recall immediately is propped up above this 60%. Before the predictions are even acted upon. So we can kind of resolve the issue before it happens. We can actually prevent model failure. And this is one of very few cases where we can actually use performance estimation together with root cause analysis to actually fully prevent model failure and make sure that not even like a single batch of data that should not be acted upon is not acted upon. And then we can also adjust downstream processes. If we cannot adjust the model or we cannot adjust the prediction thresholds, then we'll have to work with downstream processes and make sure that, let's say, the risk is still managed. For example, for credit line assignment for credit cards, we might want to just slash the credit lines everywhere to make sure to take into account that the model is worse now and it's not going to perform as well as it used to, because we're dealing with a population that's just harder to predict on. In terms of data quality, any of the issues here, we're just going to have to examine those, find out who actually supplied that data, whether the issues with data collection, with the data providers, with data engineering, or with data processing on our side. And then hopefully we'll be able to fix those issues upstream. And again, it's something that we can do hopefully quite fast before there is any significant business impact. Now, we'll be able to capture all those issues related to covariance shift and concept drift. However, there's still, covariance shift and data quality. However, there is still concept drift. And to detect concept drift, we'll actually unfortunately have to wait for the targets, which means that we still need to monitor performance and we cannot fully rely on estimated performance, even though it already helps us solve, I would say, vast majority of the issues with actual models in production. So let's talk about root cause analysis after the targets arrive or where the targets arrive. And our toolbox is the same, except it's actually expanded with covariance detection techniques. And we could do the same thing as we did before with covariance shift and data quality, but hopefully most or ideally all features that could have arisen due to covariance shift and data quality are already resolved because we captured them or we noticed them due to via estimated performance, and then we managed to resolve them. So I'm going to assume here that these issues are resolved, and I'm going to focus on the one root cause that we cannot really diagnose with estimated performance, which is concept drift. And here the flow is extremely simple. We're going to run our reverse concept drift algorithm here that allows us to quantify the impact of concept drift on any of the performance metrics of our choosing. So, F1, recall, precision, accuracy, etc. And then we're going to be able to actually quantify whether there is significant concept drift and whether there is significant impact of concept drift on model metrics. The way it works is that we're going to look at realized performance, and we see there are some alerts here. And then on the right-hand side, we're going to run the impact of concept drift on ROC-AUC. And what you see here is ROC-AUC delta, so change from the baseline. And we see that indeed, due to concept drift, we see a significant drop in performance at the same time as we see a significant drop in realized performance. So we already know that this is the root cause, which makes it actually very actionable. Before I go into how to resolve that, there is one kind of a bit more advanced idea here, but I want to still cover it because I think it's really, really fascinating. So imagine that you don't see a drop in realized performance. Everything is fine there, but you see for some reason an increase in estimated performance, which is something that absolutely might happen because it might be that the data has drifted to regions that are, let's say, further away from the class boundary, so they're actually easier to predict on. So we see an increase in estimated performance, but it is not matched with increase in realized performance, which means that there is something that's kind of pushing the performance down, even though covariance shift is pushing it up. And that something is in basically 99% of the cases, or actually maybe 100% of the cases, going to be concept drift. So if we look at the same data and we run covariance shift, concept drift detection on that, we'll see actually that there is an estimated drop in model performance due to concept drift. So you basically might want to run concept drift even if you concept drift detection, even if you don't see a decrease or drop in realized model performance, because you actually might be missing out on gains that you could have realized if you resolved concept drift, because the data actually moved to a region that's easier to predict on, but we also experience some kind of concept drift that kind of killed those gains. So now, in terms of summary here, again, we could use covariance shift and data quality tools here again, but I'm assuming that we resolve those issues using estimated performance and using the root cause analysis flow before the targets arrive. For root cause analysis flow, when the targets arrive, we're just looking at concept drift, and we might want to look at it even if there is no drop in performance, even if there is no trigger to actually trigger root cause analysis. Yeah, so that's the summary. In terms of actually resolving concept drift, this is actually the only one of these three root causes that can be reliably resolved with model retraining, and it's actually basically the best possible signal for retraining your model. So even if you don't see a drop in performance, but you see an alert due to concept drift, you should still retrain your model to get that increased performance. If you try retraining your model and you only experience pure covariance shift, That means that the data is just harder to predict on. There is less information and model input related to the model outputs. So I would not expect a significant increase in performance if you retrain the model after it experienced covariance shift. And if you retrain after observing a data quality issue without resolving it, you will probably actually cause much more problems than you might solve, because you might be retraining on the data that's actually worse quality than it used to be. That is really it. So now, just to summarize, performance monitoring needs to be done both before and after the targets arrive, but most of the root causes can be actually detected, or issues that most of the high-level root causes can be detected before the targets arrive. And in terms of our RCA toolbox, we have three main parts. We have the covariance detection algorithm, we have the concept root detection algorithm, and we have the data quality tools. And two of those, covariance detection and data quality, can be used immediately as the model makes the predictions. And also we can detect, investigate, and resolve covariance shift and data quality issues before the targets arrive, and we can actually prevent negative business impact, or at least we can very, very strongly limit it, because we can do it hours or days after the issue is found, instead of waiting months or years.